Hey everyone, this is our lesson on ideal gas law and partial pressure. So by the end of this lesson, you should be able to explain the relationships among pressure, temperature, volume, quantity of gas, and we are looking more at the quantitative side as well. So you may want to use this time quickly to go over just your basic gas laws and your gas properties before you get started. So let's first define what the ideal gas law is. So it is used to calculate number of moles in. And we do this by comparing all of our other properties of a gas, so temperature, volume, and pressure. And we do this in a formula called PV equals nRT, where R, which is the only letter that we don't know yet, is called the ideal gas constant. This is dependent on whatever your pressure unit is. So if your pressure unit is mmHg, there's an R constant for mmHg. If your pressure unit is atmospheres, there's an R unit for atmospheres. All 3 or 4 of these R units are on your reference packet, so you can look there. Ideal gases themselves do not exist. They are not a real thing. However, we can use the idea of ideal gases to compare to what we do see, which are real gases. The reason that ideal gases do not exist is because they would have no attractions or repulsions, and we know that that's not the case because gases can condense back down into liquids for a lot of substances. And then they have a negligible volume. So just kind of remember those stipulations. Real gases, though, can act most like ideal at high temperatures and low pressures. So at very high temperatures where the particles are moving extremely fast, they don't have time to be attracted or repulsed by each other, and they can spread out to take up as much volume as they want. And then at low pressures, very low pressures, that means that you have a large volume of space for the particles to move, so they can spread out without being affected by each other for attractions or repulsions. So now let's go over just quickly how to solve an ideal gas problem. And it's very important to underline and label everything that you have. Okay, so let's just use blue. At what temperature would 2.10 moles of N2 gas have a pressure of 1.25 atmospheres in a 25-liter tank? And we're looking for pressure. So we circle pressure. That's what we're looking for. That's represented by letter T. We've been given moles, so that's our N. And I know I said used to calculate moles. You can calculate any variable in that formula. If I give you moles, just go for whatever else you've got. We've got a pressure of 1.25 atmospheres, so that's P. And then 25 liters, that's our V. The only thing we don't have is our R, but again, that comes from your reference packet. So pay attention here. Your pressure unit is atmospheres. So on your table here is the very first table you'll see gas constants are, and it lists all of them. You need to find the one that has atmospheres. So I would suggest to take your paper copy and circle the pressure units that are on the top so you know which ones you're looking at. So for atmospheres, our value is 0.0821 liters times atmosphere per mole Kelvin. All right, so it's got a big unit because it's got to cancel everything out. So now that we know that, we're going to jump down and we're going to set up our calculation. So we've got PV equals nRT. We're solving for we're solving for T because that's what we want. And to do that, we've got to get rid of nR on the same side. And now we can go in and plug the values and units that we've got so we can cancel them. So remember our pressure was 1.25 atm. Oops, TM. Our volume was 25 liters. Our moles were 2.10 moles. And our pressure unit from our reference packet was 0.0821 liters times atmosphere per mole Kelvin. And again, if it helps you to write the values in first and then see what letter you don't have an answer for and move it around that way, you can. I just always set mine up first. So now that we've done that, we need to cancel the units that'll cancel. So atmospheres will cancel, liters will cancel, and moles will cancel, which is good, leaving us in Kelvin. Kelvin is a temperature, so that's what we want. So now all you do is multiply the top, equal, divide by what's on the bottom. It's 1.25 times 25, and then divide in parentheses by 210 times 0.0821. So it comes out to 181.3 Kelvin. And remember, Kelvin does not get a degree symbol, just the letter K. A big point to know here is to make sure you have the correct units. So volume always has to be in liters. If I give you milliliters, you've got to change it. We always have to have moles. So if I give you atoms or molecules, you've got to go to moles. We always have to be in Kelvin. So if I give you degrees Celsius, we have to go to Kelvin. The only one that is not necessarily particular is pressure, because you can pick your R constant to that pressure unit. But the other ones will not change. You have to have those correct units. So now I want you guys to go ahead and pause the video and try this example. Okay, so now let's talk about partial pressure. So partial pressure is the total pressure of a gas mixture, and the way we calculate that is by the partial pressures of each gas. So we have to know each individual gas to know the total pressure, or we can have the total pressure, subtract the partial pressures that we know to find the one we're missing. So your calculation is very easy for this. It's just addition. So P total is equal to P1 plus P2 plus P3, however many gases you have in the system. And it can be used to calculate the amount of dry gas over water. So we know that sometimes we'll calculate the amount of O2 over water or H2 over water, anything like that. And all you have to do there is P total minus the vapor pressure of water, which would be given in the formula, so you would not have to worry about knowing that. So let me draw that. Boop. This will be given, as with the total pressure, but I know sometimes you'll see that and might get a little anxious. So the vapor pressure of water will be given, and that's going to equal out to the partial pressure of whatever gas you have. Now, sometimes I may give you moles instead of gases, and then you're like, I don't really know what I'm supposed to do with that. You can actually set up what's called a mole fraction to figure out the partial pressure of each individual gas in the system. All you have to have are the total moles, the individual moles, and the total pressure. So a mole fraction is just going to be the moles of whatever gas you're looking at. So example, gas A, over the total moles in the system. So if you have gas A, gas B, gas C, you would add all their moles up to get the total at the bottom. But you would take just the moles of A and divide it by that total moles, or just the moles of B and divide it by that total moles. Okay. And once you get the mole fractions that you need, you're going to multiply them by the P total, and that will give you the partial pressure of that specific gas. And I'll help you set those up in a minute. So let's look at this example. It says nitrogen is collected over water at 40 degrees Celsius. What is the partial pressure of nitrogen if the total pressure is 99.42 kPa? The vapor pressure of water at 40 degrees Celsius is found to be 7.38 kPa. All right, so we want to know the partial pressure of nitrogen, which would be P into. We've been given a total pressure, so P tot, for 99.42, and we've been given the vapor pressure of water, which is 7.38 kPa. Remember that my calculation here would be the partial pressure of the gas that you want is equal to the total pressure minus the vapor pressure of water, since we're collecting it over water. And thankfully, we have all those values, so this is just a plug and chug kind of problem. So we've got 99.42 kPa. Again, you've got to make sure your pressures are in the same units, which they are here. If not, you need to convert them. 7.38 kPa. Just subtract those values. and you come out to 92.04 kPa is the partial pressure of nitrogen that was collected. So I'm going to have to erase this screen, so pause this right now and copy it down if you don't have it, because I need the space for the next problem. So now I want to read over this problem. I'm going to help you set up the first mole fraction. So I'm going to help you solve through the first one, and then you're going to do the rest of them. So it says a tank contains 5 moles of O2, 3 moles of neon, 6 moles of H2S, and 4 moles of AR at a total pressure of 1,620 millimeters of mercury. What is the partial pressure? And we want it for each gas. Okay, so you see we've got each gas there. So I'm going to set up to solve for the partial pressure of O2, and then you're going to solve for the rest of them, okay? So we know, since we've been given moles, our formula is P total times your mole fraction for O2. And that would calculate out to, very easy, we're going to take the moles of just O2, which is 5 moles, over the total moles. So we're going to do 5 plus the 3 plus the 6 plus the 4. So that would be 8 plus 6 is 14 plus 4 is 18, right? So we've got 18 total moles. So my mole fraction here is 0.278. Okay. And then you're going to take that total pressure that we were given, which was 1,620 mmHg, and you're going to take it and multiply it by that mole fraction. Which means the partial pressure is 450.36 mmHg for just O2. Now you need to do the same process for the other 3 gases. One way to check yourself on this is to then add up the partial pressures and make sure it equals that total pressure at the end. Okay? All right, guys, so now you should be able to calculate ideal gas law and partial pressures.